Alright, so hopefully finishing up lecture 15 in the next 20 minutes or so. Haha, we'll see. First of all, I mentioned that this is Euler's formula for the normal curvature in the last bit. I just like to point out that that's immediately obvious from the formula we had in the proof for g of theta. We found that a was greater than c, or equal to it, and so that identifies a as the k1 and c is the k2, and then we also showed that b was 0. So there you have it. That's Euler's formula. Then the next little bit we have left here in this section 5.2, following again Barrett O'Neill's elementary differential geometry text, is just this special case. If we think about a surface, right, and think about a point, put that point at the origin. In other words, choose coordinates, all right, that puts the surface, the point on the surface of the origin, makes the tangent plane the xy plane. So the f and the partial derivatives are 0 at the point. Then the Taylor expansion for such a function is, well, the first non-trivial thing is the Hessian term, right? The quadratic approximation to the function, second order piece. And in the text, there's an exercise which would be good for you to work. It's a little bit more. I mean, it's involved. It'd take me 10 minutes to work it out here. But for a graph z equals f of xy, you can calculate, in fact, in terms of the definitions that we've given in terms of principal curvature and shape operator, all that. And the exercise has formulas for the shape operator. When you apply those to the current context, out pops k1 is the second derivative and k2 is the second derivative of y at 0, 0, and 0, 0 respectively. Here I'm assuming x is the principal direction in which the maximum normal curvature, as usual. And so given all this, what we find then is that the surface is approximated by this, well, it could be a paraboloid, it could be a hyperboloid, right? It could be a few different things. So like, let's see here, you've got different cases, right? If you've got k1 and k2 both greater than 0, it's a paraboloid, right? So it's something like this, close to the point, right? If if both the curvatures were both negative, right, it could be like that, right? Still a paraboloid, but and then of course if you have, the product of the curvatures less than 0, then you get a saddle shape, right? Something like that. But a hyperboloid, right? If one of the principal curvatures is 0, then say you just have, say, k1 equal to 0 and k2 less than 0, then that would mean that it's like trough shaped, right? I can't draw. Trough shaped near the point, right? Because the principal curvature is 0, and then, oops, I think I drew k2 being greater than 0 in this case. And then according to the usual conventions, I guess I should say k1 greater than 0, and then k2 is equal to 0, right? So that's what I mean. Here's a couple pictures that if you assume k1's always the largest one, the picture doesn't make sense. So it's not a deal breaker or anything. It's just a question of notation, really. One of the curvatures will be largest, one will be smallest, whether it's k1 or k2. They're just labeling. All right. So that's the special case, and that's that. Moving on to section 5.3 then. So section 5.3 is on Gaussian curvature, right? And so let's get to it. It's also on a few other things like mean curvature and what's a minimal surface, what's a flat surface. All these things will be defined. So first of all, definition And I'm actually going to define two things here. For a surface, shape operator S, you can define the Gaussian curvature, which is a capital K, at the point P is going to be defined to be the determinant of the shape operator at P. And on the other hand, the so-called mean curvature is HP will be 1/2 the trace of the shape operator. Now, as is well known from linear algebra, the determinant and trace are invariant under similarity transformations. So in practice, you can of course calculate this by the determinant of the matrix of the shape operator and 1/2 the trace of the matrix of the shape operator. And it matters not really which choice of basis you use for the tangent space. In any event, we'll end up with the same determinant and the same trace, hence the same Gaussian curvature, right, and the same mean curvature. All right. All right. So, and of course there are formulas for these things in terms of the principal curvatures. Well, the principal curvatures, the max and min, you know, what did we just get done talking about? We just got done saying that, you know, the matrix for the shape operator at a point P has eigenvalues K1 and K2, right? But as is well known from linear algebra, the determinant of a matrix is what? It's the product of the eigenvalues, right? And so there you go. That's a formula for the Gaussian curvature. It's the product of the principal curvatures, the product of the, you know, min and max normal curvatures. On the flip side, the trace is the sum of the eigenvalues. This is well known from linear algebra, K1 plus K2, right? And so that's going to be equal to, well, that's not the mean curvature, that's twice the mean curvature, right? And of course this is at the point P, and this is at the point P. And these are, by the way, also the principal curvatures at the point P, at the point P, everything's at the point P. All right. So of course I invite you to, you can, it's a, you know, it's a nice little exercise of 2x2 matrix algebra to check. You can check that indeed, you know, this is the relation of the eigenvalues of a 2x2 matrix, you know, to determinant and trace, right? That's a fun little exercise. If you had my linear algebra, it may have already happened to you. I don't remember if I did that or not, but anyway, so now of course is the right time to talk about the sign of K. Oops, probably be a good time to put a page number on that. That was page 13. Now, so there are basically, you know, what are the cases? Well, you could have Gaussian curvature greater than 0. You could have Gaussian curvature less than 0. And of course you could have Gaussian curvature equal to 0. Being that it's a real value, those are kind of your cases, right? Now, Gaussian curvature being greater than 0 means that either K1 and K2 are greater than 0, or the K1 and K2 are less than 0. This means that K1, K2 is less than 0, which means one of them or the other of them is negative, right? So basically this is either one of these guys or one of those guys, assuming I'm drawing the unit normal the same way in both, right? Both upwards. So either it's like a bowl curving up towards the normal, or it's like a bowl curving down away off the normal. On the other side, if this is the situation, one of these guys, one of these saddle-shaped deals, well, then, of course, you've got one principal curvature, which is negative, one that's positive, because the surface is curving up towards the normal in that direction, and it's curving down off away from the normal in that direction. I am violating my color coding from earlier in the lecture. My apologies. And then, of course, if the Gaussian curvature is 0, that means that it's kind of boring like this. Actually, it doesn't mean that, does it? That's one possibility. How can you get a Gaussian curvature being 0? You could have K1 equal to 0 and K2 not equal to 0, right? Or you could have K1 equal to 0 and K2 equal to 0. Or I suppose you could, K2 could be, if you'll set aside the K1 has to be the largest thing for a second here. So if K1 is 0, then K2 could either be positive or negative, which means it's either a trough which opens up towards the unit normal or it's a trough which opens down off the unit normal. If both of the principal curvatures are 0, then it's called a planar point, right? All right, so, right. So I like the example that O'Neill gives. I wish I had my torus here. Oh man, I just threw out we just threw out our last donut. I think it's not quite the right shape either. Anyway, it was kind of the right thing, but you know, I'll try to draw it here. Oh, can't get my mind. So there you go. Something like this. Oh, that was an attempt at drawing a torus. Oh well. You win some, you lose some. Now, so here's I'm trying to imagine the top, the highest point, all right, assuming that the center axis is the z-axis. Here's the top point. So out here, right, if you can envision it, you've got a unit normal, which maybe points like that, right? So if you look at it, right, it's definitely a place where the curvature is greater than 0. The Gaussian curvature is greater than 0 out here, right? Because out there, the surface is bending away from that outward pointing normal. On the other hand, if you look at inside here, right? Let's say that here's the unit normal there, right? On the one kind of curve, right, if you can envision it like this, you've got the surface curving towards the normal, right? But on the other kind of curve at that point, right, the one that is wrapping like this, you've got the surface curving away from the unit normal there, right? So that's saddle shaped, right? At that point right there, because the surface is both curving towards the normal and away from the normal, depending on which principal direction you look at. So in the inside of the torus, you have k less than 0. All right, so that's all in here. On the other side of that the top point, and of course the red circle is the place where these principal curvature functions, they're continuous, right? Function's a real variable, so if it's positive somewhere, it's negative somewhere else. There's got to be a place in between where it goes past 0. And in fact, this top rim is where the Gaussian curvature is equal to 0. And those aren't planar points, right? Because if you fix one of those particular points, yeah, okay, so the unit normal looks like this, right? And if you go along that top curve, there's it's the principal curvature along that curve is 0. On the other hand, this kind of curve, the one that goes up around like that, you can see the surface is curving away. The torus is bending away from the unit normal. So I think you'd have the principal curvature is negative there, right? So Gaussian curvature is 0, but it's not a planar point. And then there's this monkey saddle, which I'll let you look at. I'm not going to try to draw that, but the monkey saddle basically is something like, it's a cubic, and it has 6 different regions, and it actually has a planar point where these different hills and valleys come together. It's an interesting example, but again, it's beyond the limits of my artistry, so let us go on. Now, there's an important lemma, and this lemma actually does come up again later in our later work. I think it's if I remember right, this is especially important to certain technical details in chapter 6. So it's worth a little bit of our time to flesh out the details here a little bit. So here's the lemma. The shape operator of V crossed the shape operator of W is equal to the Gaussian curvature at the point times V cross W. All right. And the shape operator of V cross W plus V cross the shape operator of W, well, that's twice the mean curvature times V cross W. Now these, and here we assume that V and W linearly independent in the tangent space to P at M, all right? And of course S is the shape operator. So the proof of this actually is not too hard. I think of the next thing I was thinking of that was actually a little bit subtle. This is actually pretty like duh. But proof here, so what we're going to do is we're going to say S of V is equal to, say, AV plus BW, and then S of W we're going to say is CV plus DW. So that would mean the matrix for S with respect to the VW basis would be what? It would be A, B, first column, and then CD, like that. And of course then you can see the determinant of S is what? It's AD minus BC, and the trace of S would be A plus D. Of course this is all at the point P. Great. So then you calculate S of V cross S of W. What do you get? You get AV plus BW crossed with CV plus DW. Of course V cross V is 0, and W cross W is 0, and V cross W is minus W cross V. So that gives you A times D minus B times C times V cross W, but that is of course the determinant of S times V cross W, but you know it, I know it, the people know it. That is the curvature, the Gaussian curvature times V cross W, right? And there you have it. And likewise, if you calculate S of V cross W plus V cross S of W, well, just think about it. S of V cross W, well, the B term goes away, right? And you're left with A V cross W, and then plus, well, V cross DW, right? So in other words, A plus D, V cross W, but hey, that is nothing more than, you know, that's the trace, right? But remember the mean curvature is excuse me, 1/2 the trace. So of course this is twice the mean curvature. Again at the point P. All right. Well, these are not hard. I mean, okay. The thing which is interesting, and I'm gonna just show you a little bit on how to do it. Well, I would say elegantly, but you can disagree if you want. I personally enjoy these kinds of formulas, but here's the thing. Suppose I wanted to calculate x, and I'll use vectors for a second here, x cross y. These are 3-dimensional vectors, and I want to take the dot product of that with, say, A cross B. All right, so if you'll allow me some, oh fine, I guess I'll behave, some over I of x cross y, the ith component, a cross b. Oh no, I'm violating my contravariant. I guess I should have upper i's if I want to be consistent with what I've been doing lately. Sorry. So some of, let's say I don't know, how about j, k, l, m. And so what's that? I gotta have x, xj, yk, a l, b, m, and then epsilon j, k, I, epsilon l, m, I. All right. These are just the component formulas for those cross products, right? But then there's a really cool identity which says that this thing is actually the anti-symmetrized sum of these Kronecker deltas. So this is actually the I is summed over. So like this works out to Kronecker delta JL, Kronecker delta KM, minus Kronecker delta JM, Kronecker delta, excuse me, KL. All right, and so in that it takes with it the sum over I. So you're left with sum over JKLM, and on the one hand you've got Kronecker delta JL, Kronecker delta KM, XJ, YK, AL, BM, and then you've got minus the sum JKLM, and then you got yourself a Kronecker delta JM, Kronecker delta KL, and again the X, J, Y, K, A, L, B, M. Now, okay, so let's see here. Focus on the indices which get linked. So J and L go together from that. So that links this guy to that guy. Another here, J and M go together, so that links this one to that one, right? And let's see here, K and M go together on this, which links this to that. K and L go together here, so that links these two. So what you've got then is you've got a sum over, let's say, K of YK BK, and then over here you got minus a sum over, let's say, K of YK AK, and then you got, let's see here, from the red ones you got a sum over, let's keep the L, XL AL, and over here you got a sum over, I guess I decided to keep the I'm going to keep the, what am I going to keep? I guess I'll keep the J. XJ, BJ. But of course these are just dot products, right? So what are we left with? We're left with y dot b, x dot a, minus y dot a, x dot b. Or if you like, you can write it as the determinant of this little matrix, which is what? Let's see here, we've got x dot a and y dot b, and then let's see here, y dot a and x dot b. So this is known as Lagrange's identity. If you apply this, all right, to what we just had back on the previous page, 15, all right, so again, excuse me, I had x cross y dot a cross b equals the determinant of x dot a, y dot a, x dot b, y dot b. All right. So like, say you take s of v cross s of w, right? And you take that and you calculate the dot product of that with v cross w, because v and w are linearly independent. You know that that's something non-zero. And then, you know, that is going to be equal to what? Well, that is going to be equal to, well, let's apply Lagrange's identity. This is like x, this is like y, this is my a, this is my b, right? So you get determinant of s of v dot what? A, which was v, and then x dot b, which is s of v dot w, and then over here you got s of w dot v and s of w dot w. And excuse me. Excuse me. Goodness gracious. So what does that give? What's that bring us to here? Oh. It brings us to these important formulas, which form the basis for the alphabet soup of the next section. So these formulas are the following. K, the Gaussian curvature. Oh, I know what's confusing me. I lost an important, I mean, that's fine, right? But we had something else. This was equal to what? K. K times what? V cross W. And then we're just taking the dot product of that with, V cross W, right? So this, you could also write as the magnitude of V cross W squared, right? And so you can apply Lagrange's identity in that special case to get this cool little formula for the magnitude of the cross product in terms of a 2x2 determinant. In any event, you get this formula. K is equal to the determinant of S of V dot V times S of W dot V, S of V dot W, S of W dot W, and then dividing by the magnitude of V cross W squared, which can be written as a determinant as well. It's the determinant of V dot V, W dot W on the diagonals, and then V dot W on the off diagonals. This actually comes up if you're deriving the formulas for the magnitude of the dot product and the cross product carefully. You'll run into the need for looking at these identities if you've ever gone through why it is that the magnitude of the cross product is in terms of sine theta and the dot product has that cosine theta formula. And there's also a similar formula for H, which I will write down because I don't know any better. All right, so it's the determinant, oh my goodness, these formulas. S of V dot V, S of V, if you like formulas, you should really like this section. S of V dot W, W dot V, W dot W, and then plus the determinant of V dot V, V dot W, S of W dot V, and S of W dot W, all divided by 2 times the determinant of V dot V, W dot W, oops, sorry, V dot W, V dot W, W dot W, like that. And it's the same by similar calculation to one we just went through, by almost the same calculation. Right, you just take the dot product with V cross W of, well, star star. What was star star, you ask? I'm glad you asked. Star star was this. All right. So, and while we're at it, let's call this thing star. So here we have, take dot product of star with V cross W. There we go. Okay. Now, so there's some really, really nice formulas for the Gaussian curvature and the mean curvature. And then, of course, you can relate these, you know, fun fact. And I'm starting to get tired of this section. Corollary 3.5, I shouldn't be tired. I mean, these is really, really beautiful stuff. And think about what we're doing. K1 and K2, well, these can be written as mean curvature plus or minus the square root of h squared minus k, and as O'Neill explains, to prove this, you can just see, right, that k, well, I mean, there's nothing to see here. Actually, this is our definitions. Well, it's not quite our definitions, but we already mentioned this before, right? So he just does look at h squared minus k, and what you'll get is, well, you get k1 plus k2 squared divided by 4, of course, minus k1, k2. Well, what's that? That's k1 squared plus k1, k2, 2k1, so that's over 2, right? Minus k1, k2, I'm just writing down, and then plus k2 squared. Of course, it's all right. These are over 4. It's over 4. Anyway, so that gives you plus a half. So you end up with k1 plus 2k1, k2 plus k2 squared, all divided by 4. But of course, that's what? That's k1 plus k2. So my k's look like h's. Over 2 quantity squared. And what's that mean? Yeah, it means I made a sign mistake somewhere, because that's not what he has. Minus k1, k2. Oh, duh, that's minus 1/2 minus 1 is not 1/2, it is minus 1/2. So there is a pesky minus I have neglected right here, which then goes to here, of course, as well. Alright, anyway. Sorry, I didn't mean to do this. I don't think it's that interesting. Sorry. What follows is slightly more interesting, which is the definition of flat. So, you know, what does it take for a surface to be flat? And this, I mean, it really bothered me when I first learned that a cylinder was flat. I mean, a cylinder is flat. That's weird. But there it is. I mean, a surface M is flat if the Gaussian curvature is equal to 0 on the surface, right? Surface, and these are surfaces in R3, okay, is minimal. I mean, we haven't just defined anything else. Minimal if the mean curvature is 0 on M. All right. So, examples of things that are flat, you know, a plane, flat, but also a right circular cylinder is flat because k is equal to 0, because one of the curvatures, k1 was 0, right? And k2 was minus 1 over r in this case. Now, on the other hand, the cylinder is not minimal, right? Because what's h here? Let's see here. On the other hand, of course, happily, a sphere has Gaussian curvature equal to k1, k2, right? So it's actually 1 over r squared if you work it out, right? You can go back to what we did earlier this lecture and get that explicitly. And let's see, the other thing we worked out was, oh, I guess we haven't done it. Excuse me, the saddle surface that I think we looked at explicitly at the origin, you know, the z equals xy, right? At that point, we looked at, you know, z equals xy. And if you look at it, the matrix of S that we had was E1 goes to E2 and E2 goes to E1, so that amounts to 0, 1, 1, 0. So you can see the curvature, the Gaussian curvature is the determinant of this matrix, which is -1. All right. On the other hand, this saddle surface is an example of a minimal surface, at least. Oh, but I have to have it at all points, right? I mean, I have h of the origin is 0, right? That point is equal to 0, but I don't know if the mean curvature is 0 everywhere on the saddle, so maybe it's not a minimal surface, right? The plane, on the other hand, has k equals to 0 and it has h equals to 0. That is both a flat surface and a minimal surface. The cylinder has h equal to what? The sum of the eigenvalues, right? So -1 over r. Oh, but I have to divide by 2, right? Trace divided by 2. So -1 over 2r is the minimal curvature here. Here, it would be what, 1/2 of 1 over r plus 1 over r. Actually, -1 over r to -1 over r. Because both k1 and k2 are equal to -1 over r, right? For the sphere of radius r. Every point's an umbilic point. So, of course, we get, we get -1 over r is the mean curvature here. Anyway, I suppose we have more to say about that, but I'm going to cut it off here. The next middle part of the chapter is on computational techniques, which are pretty interesting. And the last section in the chapter is really again on computational techniques, but in particular for surfaces of revolution. The section 5.5 is on the implicit case, which is also interesting, but stops short of giving you the awesome formula that I found on the Stack Exchange for a level surface. It's not in here. There's this really slick formula that's not in here as far as I don't see it in the exercises either. I'll probably give that to you as a homework. And then the more geometry happens in section 5.6 on special curves in a surface. That's probably the most important section in here in terms of terminology. The other sections that remain in chapter 5 are mostly just on just further calculational exuberance, some of which is fun. Anyway, I'll stop here. Thanks.